Today we want to talk about contour diagrams and level curves. This is us practicing picturing things by looking at topographical maps. That's what these contour diagrams, that's what level curves are. Imagine a topographical map. Now, if we're looking at a map, one of the things that we might want to know on the map is where the hills are, where the valleys are. And so we represent that on a map by drawing contour lines, drawing level curves. And we try to evenly space them. So like we'll draw a line for every, say, 10 feet of elevation if we want a very detailed one, a detailed map. Then if the lines are far apart, we can say that's not very steep. If the lines are very close together, then we'll say that's very steep. And if there's like a sheer cliff that's 200 feet, then a bunch of lines are going to come together. And you're going to say at this point here, we're at 0 feet. And at this point here, we're at 200 feet. So we're going to read that. We're going to imagine that height by looking at level curves. That's all we're doing. We're just doing that with math equation style level curves. So we're going to think about topographical maps. We're going to imagine 3D, a 2D surface in 3 dimensions by looking at a 2-dimensional representation with level curves. The reason that we want to do this is that this is how we can imagine 4-dimensional objects. We can look at the 4-dimensional objects in slices. So we want to move on to a 3D representation. Of solids in R4. This is how we're going to imagine things in 4 dimensions. We're going to have to look at it in slices that we can pull down to 3 dimensions. And it'll be very similar to what we do with a contour diagram or a topographical map. Let's start with something nice and simple. So we know that this linear equation in 3 variables is going to be a plane in R3. We know it's in R3 because we see 3 variables, X, Y, and Z, and I haven't indicated that there's some other variables secretly running around. So we're in R3. We notice that this is a linear equation. X, Y, and Z are all first-degree terms. There's a first-degree polynomial in R3. So we know it's going to be a plane. What we want to do, what we want to do is imagine what the level curves look like. To imagine a level curve, we're going to choose a fixed value of Z and see what the graph looks like. So level curve we're going to start by picking a value for Z and seeing the resulting curve. But it could be for any variable. We could see what the level curves look like in the YZ plane or in the XZ plane. But we're going to look at fixed values of Z in the XY plane. So the fixed value of the variable, this could be for
Is K
We're
supposed
gonna
to?
look at one value, pick one variable and look at a bunch of different values of that variable. Because once we plug in a number for one of the variables, we get an equation in two variables. So for example, if I fix z at 0, k represents any constant value. I use k for our constant. I like to use the mortal constant. Because every time I write it down, I get to think in my head, mortal constant. And now that's in my head. Great. So we're going to take z equals 0, and then that results in 3x plus 2y equals 0. Unsurprisingly, the contours of our plane are just going to be lines. So we have a fixed value for z. And then over here, we have the resulting curve. Yes. No, because we would write it in standard form, 3x plus 2y minus z equals 0. So the normal vector would be 3, 2, negative 1. Or if we put it the other side, negative 3, negative 2, positive 1, which is just going exactly the opposite. Yes. What do you mean? How did I picked it. We're choosing it. Just like when we first learned how to graph functions. Think way back to when we first learned how to graph functions. We just picked different values for x and plugged them into the function. That's all we're doing here. We're picking values of z, plugging them into the equation, and seeing, and then we're going to draw the result. Now, back when we were graphing functions, all we had to draw was 1 point. If y equals x squared, when x is 0, y is 0. When x is 1, y is 1. When x is 2, y is 4. All we're getting is y equals 1, y equals 4, and so on. Here, when we plug in z equals 0, we get a whole line. We get this line, 3x plus 2y equals 0. So do I really want to draw it? If I'm going to try to draw it, why am I trying to draw it? Don't try it, draw it. Don't draw it, don't draw it. I'm drawing it. Dang it. So I got a line through the origin with a slope of, let's see. I still have a hard time thinking in terms of normals, so I'm going to write this as a function. This is just going to be y equals negative 3/2 x plus 0. So through the origin with a slope of negative 3 over 2. All the x and y along this line is where z is equal to 0. So I could label that. This is the contour where z is equal to 0. If I plug in the point 0, 0, I get 3, 0 plus 2, 0 is 0. If I plug in this point, let's shrink this down a little bit. So I go down 3 and right 2. So this point is at 2, negative 3. If x is 2 and y is negative 3, I get 6 minus 6, I get 0. Every point x, y along this line will produce a z of 0. So that is a level curve for this plane. Now we're going to pick another value of z, and we're going to draw its level curve. This is analogous to us drawing a graph by picking a value of x, plugging it in, and drawing the height. So I'm going to draw the level curve where z is equal to 2. The level curve is going to be 3x plus 2y equals 2. Because I can't think in terms, I can only think in terms of slope intercept. That's why I picked 2 and not 1. Because I knew I was going to divide by 2, so I could picture the line better. Y equals negative 3/2 x plus 1. So I'm just going to take this line. That's a 2. Yeah. 3x plus 2y equals 2. So y equals negative 3/2 x plus 1. So here is the contour where z is equal to 2. So unsurprisingly, we're not getting very interesting contours when we're drawing the graph of a plane. The contours of a plane will always just be parallel lines. We can even go negative, down 1. So we're looking at just a bunch of parallel lines, but these parallel lines indicate different heights. So when we're standing at the origin, we could see we're standing at a height of 0. So if I start walking along the positive x-axis, I can see my z values getting higher. So we can see that we're going up the hill as x increases. So that's our visual representation of this plane being tilted so that these lines are higher than the other lines to the left. So we know that if we're walking along the x-axis, or if we're walking above the x-axis, we are going to be going up because we could see those z values increasing. Any questions? Is everybody okay? Now, there's nothing that restricts us to just looking at level curves for different values of z. We can also imagine level curves not over the xy plane, but say over the xz plane. So I could say, what happens when y is equal to 0? Then z is equal to 3x plus 2 times 0. So z is equal to 3x. But the same thing is going to happen. When I look at different values of y, I'm going to get a bunch of parallel lines. If y is equal to 1, then I'm going to get z is equal to 3x plus 2 times 1. Z is equal to 3x plus 2. I'm just going to be getting parallel lines because I'm replacing the y term with some constant. I'm left with an equation involving only x and z, and I can draw a picture on the xz plane. So I got a bunch of lines with a slope of 3. Then there's a third one we can do. I can fix the values of x and look at what's going on in the yz plane. The idea is we take out one of the variables, we represent it with a constant, and we do that a bunch of times. The same thing that we did when we graphed functions. In an equation with 2 variables, plugging in a value for one of the variables left us with variable equals constant. And we just represented it with a dot. If we take an equation with 3 variables, choose a fixed value for one of the variables, we end up with an equation in 2 variables, and we know that that will make a one-dimensional curve in 2-dimensional space. We're just going to have to do this. We're going to go do this going forward. If I have an equation with 4 variables, so now we're looking at stuff in R4. If I replace one of the variables with a constant, I get an equation with 3 variables, and that's going to be something in R3. How's everybody okay? I hope I added one throughout those properly. It's dangerous because I don't edit videos, because then I would have to watch the video and then like listen to the video, and that would be listening to my own voice, and no one likes to do that. You know what I mean? That's why when I hit record, there's that long pause at the beginning, because I don't want to accidentally be like uploading and then like hit play on the video. I can stop it before I hear myself talk. So the way when we think about drawing level curves, it's the same process as graphing a function by plugging in values. It's the same process as graphing y equals f of x by plugging in a bunch of x. But instead of getting 0-dimensional values in 1-dimensional space, we're getting 1-dimensional curves in 2-dimensional space. Now, if you recall, we didn't want to have to plug in values all the time to figure out what stuff looks like. I need to be able to say y equals x squared, and everybody needs to picture a parabola right away. I need to be able to say x squared plus y squared equals 1, and I need you, everybody needs to picture a unit circle right away. I need to be able to say y equals 1 over x, and everybody pictures that hyperbola right away. We have to recognize shapes based on their equation. The same thing is going to happen here. We're going to have to recognize shapes based on the equation. So our job is to recognize shapes based on the equation. We still have this job. Recognize a shape based on the equation. When I write y equals mx plus b, you think line. When I write y equals ax squared plus bx plus c, you think parabola. When I write x squared plus y squared equals 1, you think circle. Specifically unit circle in this case. You have this whole library of functions that you can picture based on the equation. All we need to do now is add a variable into the mix and see what we get. We've already started. Z equals Z naught plus MX plus NY plane. We need to get some more. Any questions? How's everybody okay? Everybody looks concerned. Are you concerned? Or is it just too simple? It's hard to tell because like when class is all easy and everybody's like, oh, we got it. You know, you don't have to go so slow, go faster. Let's do some more stuff. It looks like this. But when class is like really hard and I'm talking about nonsense and nothing makes any sense, you look completely different. You all look like this. So, and I know some students are like, I don't want to use my voice to ask questions. So I'm going to put on my I have a question face and hope that Leach notices. And so you put on your I have a question face, which looks like this. And then after class, you're like, oh man, Leach just completely ignored me during class. I'm going to rate my professor. Leach sucks. Ignores student requests. Refuses to read mine. I'm just kidding. I just can't tell you that I'm reading all your minds. And I call Leach, you can't read students' minds. I'm like, oh, that's right, I can't. It's like, oh, no, we're not saying it like that. We're saying you're not supposed to be doing that. I'm like, oh, all right, I won't. Wink. It's like, oh, no, stop doing that. Like, oh, no, I got it. I will definitely stop doing that. And they're like, oh, Leach, please stop saying it that way. I'm just kidding. I can't read your minds. What? It's funny because we joke about like being telepathic and shit like that. And we are. Like, how many times have you like, hey, what's wrong? Nothing. And you know there's something wrong. You just read the whole communication, right? You didn't listen to the words. You're like, oh, no, it's fine. So, oh, that definitely means it's not fine. You know what I mean? Yeah, that's psychic. It's just psychic ability. It's just not reading minds like we think about it in the movies, where you like listen to someone's thoughts and the thoughts are coming through like full sentences. thoughts don't come through like full sentence. Thoughts are a jumbled mess of garbage. If you could actually hear other people's thoughts, you would probably just go insane. That would be the worst thing ever. You know what I mean? Have you ever just stopped and listened to the garbage that goes on in your head? Just like stop for a while and listen. Maybe it's just me. I don't know. What are the level curves in Z going to look like? If I choose fixed values of Z, what are the curves going to look like? Circles, right? Because we got our we got our library of functions that we can picture. And when we see things like x squared plus y squared, that's going to make circles. What are the level curves going to look like now? Remember, fixed values of C. What is it? Not quite. No, we can't distribute exponents over sums. Square root of x squared plus y squared can't simplify. It's hard to tell, right? We know something happened. Let's pick certain values of Z and find out what's going on. We know that if I take like y, if I have y equals the radius minus x squared, that's going to be in the top half of the bottom half because we can't make a function for a circle. Yeah. So let's see what happens here. Remember what we initially stipulated. I want fixed values of Z. So fixed values of Z. So the contours are circles. So what happens when Z is equal to 0? What do we get over here? Just a point, right? You set it zero dimensionally. That's why I couldn't hear it. This is just going to be the origin. There's only one point that fits this description. That's just the origin. Let's see. If Z is equal to 1, then I get the equation x squared plus y squared is equal to 1. If Z is equal to 2, then x squared plus y squared is equal to 2. So just like we expected, all the contours are circles. This is a circle of radius 0. Here's a circle of radius 1. Here's a circle of radius square root of 2. Yeah. Not quite. Let's find out. What we're going to do is we're going to go back to our old technique. Always go back to the old technique. Still functional? Yeah. Okay. So let's look at the other one. We want to know what the contours look like. So for fixed values of Z, so contours are what happens when Z is equal to 0? I get the square roots of x squared plus y squared is equal to 0. What's this shape going to be? It's just a point. Let's see, if Z is equal to 1, then the square root of x squared plus y squared is equal to 1. What's this shape? It's a circle. What's that square root doing? Not quite doing plus or minus. Plus or minus is a square root thing that shows up when we're solving equations. But I can rewrite this equation without the square root by doing what? This equation is the same as x squared plus y squared is equal to 1. What if z is equal to 2? Then the square root of x squared plus y squared is equal to 2. What equation is that equal to? Without the messy stuff. The 4 on the other side. We'll square both sides, and this will give us the equation x squared plus y squared is equal to 4. So over here, we get a radius of 0, then a radius of 1, then a radius of 2, and if z is equal to 3, our contours at x squared plus y squared is equal to 9. So we get a radius of 3. But the contours themselves are still just circles. The difference happens in how the circles are spaced apart and the kind of circles that we're getting. When z is equal to 0, they look the same. That doesn't help. When z is equal to 1, in both of them, we're at the same circle of radius 1 centered at the origin. But when z goes up to 2, when z has gone up to 2, in the z equals x squared plus y squared, our radius is square root of 2. But our radius for the square roots of x squared plus y squared has gone up to 2. So we got a bigger circle at that height. So in both cases, the contours are circles. Questions? This means something is going on in the other direction. We can see that the circles here are getting closer together than the circles over here. Here, when z is equal to 3, my circle's all the way out to a radius of 3. When z is equal to 4, my radius will be 4. When z is equal to 5, my radius will be 5. But over here on the non-square root one, z goes up by 1, and the circles are getting closer together. My radius goes from 0, then 1, then the square root of 2, which is about 1.4, root 3, which is 1.7, root 4, which is 2, root 5, which is 2.2. My circles are getting closer together. Let's look at this from another side. Let's think about the level curves from another direction. We've got symmetry with x and y, so I'm just going to pick x values. Or do you want to do y values? Do you have a preference? No one has a preference? X and y are just all the same. That's correct. It's symmetric. If x is equal to 0, then we get the equation z is equal to 0 plus y squared. So z is equal to y squared. What's that shape? That's a parabola. Over on the other side, when x is equal to 0, z is equal to the square root of 0 squared plus y squared. What's that equal to? Because we're trying to picture it. Oh, no, you're telling me why. I get it. Is it really just y? If I square something and then find the square root, I'm just going to get that value back? Like if I take -2 and square it and then take the square root, I'll be back at -2. That'd be a +2. So we're going to end up with the absolute value. When we look at it from the side, we can see that the non-square root one, it looks like a parabola from the side. But the square root one looks like an absolute value from the side. So the square root one is giving us a cone, and the non-square root one is giving us this parabola. The sides are looking like parabolas. Can you picture it? It's great that we don't have to picture it because we can see what the slices look like. See, I got Wolfram Alpha like bookmarked. Oh, I should share. Non-square root one, let's take a look at that. And we can see it's got this parabola shape. You can see this parabola shape. Look at it from the top. We can see those circles getting closer together. Now, let's look at z equals the square root of x squared plus y squared. Hard to see with the resolution, but now look at the contours from the top. We still get circles, but instead of the circles getting closer together, the circles are evenly spaced, because when we look at this from the side, we're just getting a cone, and we've got this line, this V-shaped line. Yeah. Oh, from Google? Google's stealing everything. So it just says graph z space z equals. Ah, dope. Can you move it? Can you turn it? Twist it? Wow. That is pretty awesome. And if we get rid of the squirts, we can see the parabolas from the side. It's got to be at this funky Batman. Oh, wow, zoom. Oh, great. It zooms and scrolls at the same time. That's all right, Google. I forgive you. That's pretty dope. Oh, thanks for that tip. Any questions? All right, so what we're trying to do is build a new library of surfaces. We want to be able to look at an equation and see what the surface is in our mind. All right, that's it for today. I will see you all on tomorrow. Oh, no, I'll see y'all on Monday. Office hours tomorrow from 9 to 11 on Zoom or in my office. That's it for today. That's it for this week. I'll see y'all on Monday. Everyone have a good day, and thanks for playing.